by Floer theory.
Thanks, Mina, and thanks for the invitation to give this talk to all the organizers. So I wish I had exciting new results on Khovanov homology, but I don't. So I'm going to be, at the end, I'll update a couple of things, but mostly I'll be telling you about things that are a little bit older. So I'll be talking about the Jones polynomial of a knot and its refinement known as Khovanov homology. The first to make a physics-based proposal for Khovanov homology were Gukov, Vafa, and Schwartz in 2004. And they suggested that vector spaces associated to knots that a few years earlier were proposed by Ugri and Vafa were related to what appears in Khovanov homology. I re-expressed this construction a few years later in terms of gauge theory and the counting of solutions of partial differential equations. And that's the story I'll describe today. And I've given a variety of lectures on this, several versions of which are available online. And today's lecture is closest actually to the last of these three. In any event, the goal is to construct invariants of a knot in R3, or more generally a link. In the simplest version, the invariants will be obtained by counting with signs the solutions of an equation. The solutions will have an integer value topological invariant P. And if AN is the number of solutions counted with signs with P equals N, then the Jones polynomial of the knot is going to be the sum of AN Q to the N. Now, to get Khovanov homology, the situation should be categorified. That means for each N, we want a complex of vector spaces whose Euler characteristic is A sub N. Now, as far as I know, you can only categorify the counting of solutions of an equation if the equation is the equation for critical points of some Morse function. At any rate, that's what categorification is going to mean in this lecture. So our equations will be PDEs in a certain dimension. So H will be a Morse function that depends on functions in that dimension, the functions that appear in the PDE. And the gradient flow equation of Morse theory will be an equation in one dimension more. But let's put aside categorification for a moment and assume we were just trying to describe the Jones polynomial. Now, the equations whose solutions I claim we should count to define the Jones polynomial and eventually Khovanov homology might look ad hoc if written down with no explanation of where they come from. And one approach, which actually has been my approach in various lectures, is to explain the physical setup and try to deduce from there what we should do. And I could have considered doing that today. Not everyone would find it helpful, although I'm sure some of you would in this audience. Instead, I'll take a different approach where I motivate the equations from what appears in a known mathematical approach to Khovanov homology, at least in its singly graded version, which is symplectic Khovanov homology, developed by these authors, among others. And there probably are more recent references I should be citing. So going all the way back to von Jones's original work, most approaches to the Jones polynomial define an invariant in terms of some presentation of a knot. For example, you consider a projection to a plane, like I've actually drawn because it's hard to draw a knot without depicting it with a projection to the plane, or some other knot presentation. Then you define something that's manifestly well-defined when you're given a presentation. And the magic is to show that the choice of the presentation didn't matter. That's never obvious, and that's where the magic is. And there always is some magic. Now, an approach based on counting solutions of PDEs has the opposite advantages and drawbacks. While topological invariance would be manifest, given certain generalities about elliptic PDEs, and assuming compactness is under control. But it might not be clear how to calculate. Of course, the ideal is to have manifest 3, or in the categorified case, 4-dimensional symmetry, together with a method of calculation. How might we achieve this? So the way I'll interpret this question is the following. Suppose we have a PDE with the property that counting its solutions gives the Jones polynomial. What further property should that PDE so we would have a good way to count the solutions in practice? Now, we'll adapt what's been done mathematically in many problems that involve counting of solutions of PDEs. So a natural try is to stretch a knot in one direction. So here's a highly stretched knot that's been stretched in one direction, which I've called the U direction. In other words, the stretch direction is parameterized by a real parameter U. And one wants it to be the case that except near the ends, the solutions are independent of U. Now, not every PDE is going to have that property. So I haven't told you what the PDE is or how the knot enters the PDE, but there'll be a PDE and the precise conditions you want on a solution will depend on the knot. And then you want it to be true that when you stretch the knot, you get a solution that's independent of U except near the ends. We won't get that for free. And in fact, with Gaiotto, we had trouble getting it. We had to include a perturbation of the simplest version of the equation we wanted to study in order to make this true. Well, if it is true, well, whether it's true or not, but it's most useful if it is true, we define a space M of U independent solutions. We can think of these as the solutions in the presence of infinite long strands that extend in the U direction. So we have a link, well, a non-compact link that looks like this, just a lot of parallel strands in the U direction. Whatever our equations are, we consider the U independent solutions. And the space of such solutions, I've called curly M. Now in M, we define two subspaces, L sub L and L sub R, consisting of solutions that extend over the left or over the right. For simplicity in my terminology, I'll assume a given solution extends in at most one way, but that's not really necessary. But if it's not true, it's technically more complicated. For example, a point in L sub L represents a solution in a semi-infinite situation where the strands terminate on the left but go to infinity on the right. And the point in L sub R would represent the opposite. Now, if we have a global knot with the strands that end on both ends, I keep saying knot, but it could be a link. A global embedded one manifold that looks like this, where the parallel strands somehow end at both, are terminated at both ends. The global solutions are simply the solutions in the middle that extend over both ends. So the global solutions are intersection points of L sub L and L sub R. The integer an that appears as a coefficient in the Jones polynomial is going to be the algebraic intersection number of L sub L and L sub R, which will be the count with signs of the solution of the global equation in the presence of the knot. To be more exact, an is this intersection number where we only count intersections where the topological invariant P is equal to n. Now, in the language of intersections, categorification can happen. Well, how can categorification happen? So we have an M, and it has two sub-varieties, L sub L and L sub R, and we took the intersection number. We want to categorify that intersection number. Well, where has the intersection number of two submanifolds been categorified? That's what Floer did in Floer theory. So categorification can happen. And I mean here the original version of Floer theory for symplectic manifolds. So categorification can happen if M is a symplectic manifold and L sub L and L sub R are Lagrangian submanifolds. Then Floer homology, in other words, what physicists would call the A model or mathematicians would call the Fukaya category of M, will give a framework for categorification. Now, from the point of view of today's lecture, the reason all this will happen is that even before we stretch the knot to reduce to intersections, the equation whose solutions we were counting are equations for critical points of some Morse function h. Physicists call it a Morse functional because it depends on fields, that is, infinitely many variables. But it's a Morse function in an infinite dimensional situation. It'll be an middle dimensional Morse function in the sense of Floer theory. So, but we'll come back to that eventually and we'll categorify. Now, anyway, that's the framework we want to head for. In heading for it, well, as I said, we could have started with the physical setup, but instead of starting, and that would have been clear to a certain fraction of the audience. Instead of starting with the physical setup, I'll start with something else, which I hope will also be clear, at least to a fraction of the audience. So a known approach is symplectic Khovanov homology, which, at least in a singly graded version, describes Khovanov homology in terms of Floer theory for a very specific M. So a description of this M that was proposed by Kamnitzer and exploited in a mirror version by Kaudist and Kamnitzer, and which was part of the guide in my work, is the following. M can be understood as a space of Hecke modifications. So again, some of you probably are quite familiar with Hecke modifications and may know much more than I do, but I presume not all. So I'm going to spend some time explaining what's meant by the phrase a space of Hecke modifications, and also, very importantly, what it has to do with PDEs. So here, C is going to be a Riemann surface, and G for me is a compact gauge group. But when we discuss Hecke modifications, it's important to consider the complexification. So G sub C is the complexification of some compact Lie group G. And E will be a holomorphic GC bundle over C. Now, a Hecke modification of E at a point P in C is another holomorphic GC bundle E prime over C that's presented with an isomorphism to E away from P. It's not just isomorphic to, there isn't just the statement isn't just that E prime and E are isomorphic away from P, but you're presented with the isomorphism. So the Hecke modification is the pair consisting of E prime and this isomorphism. So for example, what could such a Hecke modification be in a simple case? Suppose that GC is C star, the complexification of U1. Then we could think of E as a holomorphic line bundle over C. A holomorphic line bundle L prime that's isomorphic to L away from P is obtained by twisting with what's called O of P to some integer power, where O of P is the line bundle whose sections are homomorphic functions, except that they're allowed to have a simple pole at P. So we modify, a section of L prime is the same as a section of L, except it's allowed to have a pole of order n at P, or maybe it's required to have a zero of order minus n if n is negative. So that's what would be meant by Hecke modification in the Abelian case. Now here, the integer n can be thought of as a weight of the Langlands GNO dual group of C star, which is another copy of C star. So the weights of C star are integers, and here a Hecke modification at a given point is labeled by an integer. And well, an insight in different ways of Langlands and Goddard and Witten is that the weights that will arrive when we make these modifications are weights of a dual group. So the reason I call the Lie group here G sub C is that when we do gauge theory, the gauge group will be the compact real form, which I'll call simply G. Now, in general, for any G, there is a corresponding Langlands GNO dual group, which I'll denote by this symbol, and I'll just call G dual, with the complexification G dual sub C, such that Hecke modifications of the holomorphic GC bundle at P occur in families classified by dominant weights or equivalently finite dimensional representations of the dual group, or equivalently its maximal compact subgroup, since the dominant weights or finite dimensional representations of those two are in parallel. For example, well, let's consider what's perhaps the simplest example. Suppose that the complex Lie group is GL2C. Then we can think of it, then we can associate to a GC bundle a rank 2 complex vector bundle E over C. What would be a Hecke modification of such a rank 2 bundle? Well, I'll answer that in a second, but first I'll say that one thing that makes this example simple is that the Langlands GNO dual group is the same thing again. And this, well, a minimal representation of the dual group is the two-dimensional representation. And a Hecke modification dual to the two-dimensional representation is as follows. Locally, we can trivialize E and write it as the direct sum of two trivial line bundles O. in a neighborhood of the point P where we're planning to make the Hecke modification. And then we could say that in the same local decomposition, E prime is O of P plus O. So O of P plus O is a rank 2 bundle that's isomorphic to E away from P with an obvious isomorphism. And that isomorphism will extend over the rest of C, even though this description didn't, or might not have. So that's an example of a Hecke modification of a rank 2 bundle of a minimal type. Minimal type means it's dual to this 2-dimensional representation. The difference from the Abelian case is that there's not just one Hecke modification of this type at P, but a whole family of them arising from the choice of decomposition of E, rather as O plus O. So because of the dependence, well, what we really did here was we picked in which direction. The decomposition as O plus O wasn't important. What was important was the first summands were without a pole. And so because of that dependence on the choice of that first summands, the Hecke modifications of this type at P form a family parameterized by a copy of CP1. Now suppose we're given two endpoints on well, I'll take our Riemann surface for the moment to be the complex plane, which is the same as R2, but viewed as a complex manifold. And we're given two endpoints on which we're going to make Hecke modifications of this type of a trivial rank 2 complex vector bundle E over C. So in this case, I've labeled 6 points in the plane. The space of all such Hecke modifications would be a copy of CP1 to the 2n with one copy of CP1 at each point. However, there's a natural subvariety M inside CP1 to the 2n, which is defined as follows. Well, let's add a point at infinity to compactify C to CP1. So now we're making Hecke modifications of a trivial bundle, O plus O over CP1. Now we have this family of Hecke modifications, CP1 to the 2n. But generically, when we extend them over CP1, okay, so we have this family of Hecke modifications of a trivial bundle over CP1 that makes a new bundle over CP1. By consideration of the first Chern class, you'll see that this new bundle is generic. It has first Chern class 2n, because the first Chern class changed by 1 with each Hecke modification. And that means it's generically going to be the direct sum of 2 copies of O of n. So we can, by insisting that it has the generic behavior, we get a submanifold of this thing. So what I described here slightly differently. We can twist back to 0 first Chern class by twisting E prime by O of minus n times the point at infinity. This is then a rank 2 bundle over CP1 of 0 first Chern class. It's generically trivial. And if we ask that it actually is trivial, we get a Zariski open subset of CP1 to the 2n. If we'd been working in PGL of 2C rather than GL of 2C, we wouldn't have needed this twisting, and we would have defined M by just saying that E prime is trivial. Now, this M that I've described is the M which is used in symplectic Khovanov homology, at least for this case of the 2-dimensional representation of the dual group being SL2. So symplectic Khovanov homology, at least in that example, is constructed by considering intersections of Lagrangian submanifolds of that space I just described, the space M of multiple Hecke modifications from a trivial bundle to itself. So that was an algebraic geometer's description of that space. But remember, our goal was to get a description of the Jones polynomial and Khovanov homology, where topological invariants will be more obvious than they might be in other approaches. For that, we want to describe the space of Hecke modifications in terms of PDEs. So we want to describe the same space M as the space of solutions of some PDE. Well, in the work I did with Kapustin on gauge theory and geometric Langlands, it was an important fact that M is a moduli space of a certain solution, of solutions of a certain system of PDEs. But there's a trick. It's displaced in dimension by 1 from what you might expect. So the algebraic geometer's definition of M involved bundles on a 2-manifold R2, which was simply the complex plane in the example I gave. Or we compactified it to CP1, but anyway, it was 2-dimensional. But the PDEs are going to be in 3 dimensions. There'll be PDEs on R3. As a result of this, everything in the rest of the lecture will be in a dimension 1 more than you might expect. So to describe the Jones polynomial, an invariant of knots or links in 3 space, we'll count solutions of some PDEs in 4 dimensions. And the categorified version related to Khovanov homology will involve PDEs in 5 dimensions. The 3-dimensional PDEs that we need are known as the Bogomolny equations, which were originally introduced to describe magnetic monopoles in gauge theory. They're equations for pair A and phi. A is a connection on a G bundle E over a 3-manifold, and phi is a section of the corresponding adjoint bundle. In other words, it's a 0 form valued in the adjoint bundle. And if we write the Yang-Mills curvature as F equals dA plus A wedge A, then the Bogomolny equations are like so. They say that the curvature is the Hodge star acting on d sub A of F. D sub A is the gauge covariant exterior derivative. So these are elliptic differential equations modulo the gauge group, and there's a vast literature in them from many points of view. For example, Atiyah and Hitchen wrote a book called Physics and Geometry of Monopoles, which was about these solutions of these equations. And there's much, much more from many points of view. So the Bogomolny equations have many remarkable properties, but for today, we'll focus on just one aspect. We'll consider the Bogomolny equations on a 3-manifold, which is a Riemann surface times R. Well, any connection A on a G bundle over a Riemann surface determines a homomorphic structure on E, or more exactly on its complexification. You simply write the connection as a 0,1 part plus a 1,0 part, and you use the 0,1 part of the connection to define the complex structure of the bundle. In complex dimension 1, there's no integrability condition for a d-bar operator. So whatever the connection is, d bar A defines an integrable homomorphic structure on the bundle. So in particular, if you have a gauge field over R times C, you could specialize to any point Y in R, and then you could restrict any G bundle with connection over R times C to Y times C, and that'll give a homomorphic bundle E sub Y over C. But if the Bogomolny equations are obeyed, E sub Y is canonically independent of Y. Indeed, a consequence of the Bogomolny equations is that the 0,1 part of the connection is independent of Y. This should be Y, not R, up to conjugation. If we parameterize the real direction in W3 by Y, then part of the Bogomolny equation is this. So the Bogomolny equations, they're equations for one form in 3 dimensions. So there are 3 real equations, but 2 of the 3 real equations can be put in the form of this one complex equation. And this one complex equation tells you that up to a gauge transformation generated by minus I phi, d bar A is independent of Y. So the Bogomolny equations, if we have a solution everywhere on R times C, would give us a constant family of homomorphic bundles over C. Well, we don't want a constant bundle family there. We want a family that undergoes jumps due to Hecke modifications. The Bogomolny equations admit solutions with the singularity at isolated points in R3 or in a more general 3-manifold W3. So let me first describe the picture for U1. You fix an integer n, And you observe that the Bogomolny equation has an exact solution for any point in R3. Phi is n over 2 times the distance from that point x0, and f is star d phi. So this formula, this was the Bogomolny equation. But we have to remember that f was supposed to be the curvature of a connection. And this formula defines a closed two form. Well, you need to know that this phi is harmonic. It's harmonic. It solves the Laplace equation away from x equals x0 because this is the potential due to a point charge. So it's sort of the fundamental solution of the Laplace equation with a point singularity. So star d phi is therefore closed. But for f to be the curvature of a connection, the period of f, that is, its integral over a two-sphere that surrounds the singularity, has to be an integer multiple of 2 pi. And that's why n has to be an integer. So therefore, for every integer n, this is a solution of the Bogomolny equations for u1. So this sentence is what I just told you. The formula is to find f and not the line bundle and the connection A on that line bundle whose curvature is f, but they exist if and only if n is an integer. Now for g equals u1, since the Bogomolny equations are linear, they have a unique solution with singularities labeled by specified integers at specified points in R3. So this is an attempt to draw R3 with some points in it that have been labeled by integers. Now I'm going to assume the integers add up to 0, which is it's the condition that the given solution vanishes at infinity faster than 1 over r, I guess. Now we pick a decomposition of R3 as R times R2, and we identify R2 as the complex plane. Let's say the singularities are at yi times pi. Yi is in R and pi are some points in C. Well, as long as y is not one of the bad points, the indicated solution of the Bogomolny equations determines a homomorphic line bundle L sub y over C, and this naturally extends to L sub y over CP1. That's where we need the sum of the n's to be 0, so that the solution vanishes fast enough at infinity that the line bundle naturally extends over CP1. L sub y is constant up to isomorphism for y not equal to one of the yi's. Because when y isn't one of the yi's, the Bogomolny equations are satisfied and they make L sub y independent of y as a holomorphic bundle, as I explained. But even when y crosses one of the yi's, the argument still works as long as you keep away from the bad point pi in CP1. So the holomorphic type of Ly jumps when you cross the bad point, which was at y equals y sub I, but it doesn't jump if you remove the 1 point p. So this means that by definition, the jumping of the bundle when you cross the bad point is a Hecke modification. So in this Abelian case, by consideration of the first term class, you can determine what the Hecke modification is. The Hecke modification when you cross the bad point is precisely the most general Abelian Hecke modification at the point pi. Now, since I took the sum of the charges to be 0, Ly is trivial. At either end, y goes to minus infinity or plus infinity. So this solution of the Bogomolny equation describes a sequence of Hecke modifications that starts and ends at the trivial line bundle. So that's the Abelian version of what we want as the space M that we will use for the Jones polynomial and Khovanov homology. We can do something similar for any simple Lie group G. This construction was introduced by 't Hooft more than 40 years ago, and it's important in physical applications of quantum field theory. You let T be the maximal torus of G and little t its Lie algebra. You pick a homomorphism rho from U1 to T. Up to a Weyl transformation, such a rho is equivalent to a dominant weight of the dual group G dual. That was, I think, closely related to Langlands' definition of the dual group. And what Goddard-Neutzonov said was even closer to what I'm saying. So it corresponds to a representation R dual of the dual group. So now we turn the singular solution of the U1 Bogomolny equations that we already used, but for the case n equals 1, into a singular solution for G by simply mapping U1 to G via this embedding row. So that way we get a singular solution with a point singularity at a chosen point, and the singularity, the type of singularity, is labeled by this representation of the dual group. Then we look for solutions of the Bogomolny equations for G with singularities of this type at specified points yi times pi in R3. I said this type, but we are allowed to use a different row for each I. So the points, we have a lot of points in R3. Each point is labeled by, in general, a different representation of the dual group. So the picture is the same as before, but instead of labeling the points by integers, they're labeled by representations of the dual group. In this example, points row 1, row 2, row 3, row 4. So the points are labeled by homomorphisms from U1 to the maximal torus, or in other words, by representations of the dual group. Also, now we must specify that we want a solution that goes to 0 infinity faster than 1 over r. In the Abelian case, that was equivalent to a condition on the representations. The sum of the ends should be 0. On the non-Abelian case, no matter what the representations are, we need to impose this condition. Now, given this, such a solution describes a sequence of Hecke modifications at pi of type rho I, mapping a trivial G bundle over CP1 to itself. So this space is actually a Hyperkähler manifold, essentially first studied by Peter Kronheimer in the 1980s. And we can view it as a Hyperkähler manifold, but for today, we're going to only view it as a complex symplectic manifold. So if we pick a decomposition of R3 as R times R2, that picks one of the complex structures on the Hyperkähler manifold. And in that complex structure, M is the moduli space of all Hecke modifications of indicated types at the indicated points, mapping a trivial bundle over CP1 to itself. So you can use this construction to explain various properties of spaces of Hecke modifications. But for today, we want to focus on the fact that for the application to knot theory, we want M to be the space of U-independent solutions of some equations. So M I defined as a space of PDE, solutions of some PDEs, but they were PDEs in 3 dimensions. And they weren't independent of any of the 3 coordinates in that picture. They depended on the choice of a finite set of points. That's not translation invariance in any direction. But we want to have a picture like this, where M, we have some PDEs, and the U independent solutions are supposed to correspond to M. Well, we described M by solutions of some PDEs on R3. So now we will have to think of M as a space of U independent solutions on R3 times R, where the second factor is parameterized by U. And then we're supposed to get back to this picture here if we look at only solutions independent of U and then forget about U. So, well, this is a non-trivial fact. If you take a generic PDE in D dimensions, good luck in regarding its solutions as the U-independent solutions of some elliptic PDEs in D plus 1 dimensions. That's only going to work on a very good day. I hope what I'm saying is clear enough that that last statement is clear. But in this case, there actually are natural 4-dimensional PDEs that work, sometimes called the KW equations because they had appeared in my work with Kapustin. There are equations for a pair that I'll still call A and phi, where A is a connection on a G bundle over a 4 manifold now, and phi is now a 1 form on the 4 manifold, valued on the adjoint bundle. So anyway, these are the equations. And those are, again, elliptic equations modulo the gauge group. And in a special case where the 4 manifold is W3 times R, or W3 is a 3 manifold, a solution being independent of U means that A is a pullback from W3. And then we assume that phi takes this form where this phi is also a pullback. Then these equations reduce to the Bogomolny equations. So our space of solutions of the Bogomolny equations are the U-independent solutions now of some equations in 4 dimensions. So the singular solution of the Bogomolny equations that we've already studied can be embedded. In other words, the one represented by this picture, it has singularities at points. But when we add a 4th dimension, the points became lines. So now we have a solution of a 4-dimensional equation with a singularity along a line rather than a point. And in fact, this is an elliptic situation. So, I described the local model for the singularity, but you can generalize it. In general, if Y4 is a 4 manifold and S is an embedded 1 manifold labeled by a homomorphism from U1 to the maximal torus or by representation of the dual group, then it makes sense to look for solutions of the KW equations on Y with the singularity of the indicated type along S. And you can count, well, if you can resolve some compactness issues, which are actually highly non-trivial, then you can count those solutions weighted by signs and get an integer that will characterize this situation. So we can do this in general on Y, but now if we specialize to this case that the solution is independent of one coordinate, then as I've already said, the U-independent solutions are parametrized by this space M of solutions of the Bogomolny equations. And moreover, you can show that these are all the solutions that have reasonable behavior at infinity. So in this stretched situation, the solutions are going to become independent of U and will reduce to, a solution will reduce to one of the solutions of the 3-dimensional equations. So what do we have so far? We have an elliptic PDE in 4 dimensions. We have an interesting way to specify what singularity it should have on an embedded circle. And we can even count solutions. Well, we can hope to count solutions, modulo some subtle technicalities in that situation. But this sounds like a ridiculous framework for knot theory because there's no knottedness of a 1 manifold in a 4 manifold. So what are we talking about? Well, a couple of things are missing from what I've said so far. There are a few directions to go next, but I want to head for categorification, which will also resolve the point I just mentioned. In heading for categorification, I'm going to first get what's called the singly graded version of the theory, which is the version which is graded by the cohomological grading, but no Q grading. That's the version of symplectic Khovanov homology as developed by authors I mentioned at the beginning of the lecture. I'll very, very briefly mention what one has to do in the framework I'm talking about to get the Q grading, but there won't be time to do justice for that. So what is categorification going to mean? Well, I briefly said a word about that at the beginning, but let's go in more detail. Let's practice with an ordinary equation rather than a PDE. Suppose we're on a finite dimensional compact-oriented manifold N with a real vector bundle V over N, and we're given a section. So we can define an integer by counting with multiplicities, in particular with signs, the zeros of S. That integer is the Euler class of the bundle V. So that's an equation, namely S equals 0. So it wasn't a PDE. It's an equation. Since we are on a finite dimensional manifold N, the condition S equals 0 is an ordinary system of equation for finitely many variables, not a PDE. But we're practicing with ordinary equations, that is, equations for finitely many variables, as opposed to differential equations. Now, in general, as far as I know, you can't categorify the Euler class of a vector bundle. I'm not sure what it's supposed to be. But suppose that the vector bundle is the cotangent bundle, and the section is the differential of a Morse function. Then the zeros of S do have a natural categorification that's described in what's sometimes called Morse homology. You define a complex V with a basis vector size sub p for every critical point P of H. Here I'm going to assume for simplicity that the critical points are non-degenerate. The complex is Z-graded by assigning to each size sub P the index of the critical point P, and it has a natural differential that's defined by counting gradient flow lines between critical points. So concretely, I think I might have Q and P backwards here. Well, what I've written is the D of psi P. Okay, D of psi P is the sum over Q of NPQ times psi Q, where the sum runs over all critical points Q. This Morse index is one more than that of P, and NPQ is defined by counting flows from P to Q. So I guess with what I've written, I think what I've written is internally consistent. A flow is a solution of a differential equation in one dimension. It's the gradient flow equation. To define it, you pick a Riemannian metric on the manifold N, and then you can write down this equation that the x dt is minus the gradient of H. And counting its solutions, you get these integers N, and they make the differential whose homology is Morse homology. The complex you get is independent of the metric up to quasi-isomorphism. What you count are actually one-parameter families of flow related by time translations, that is, by constant shifts of the parameter t in the equation. So in this way, not any equation for finite many variables, but the equations for critical points of a Morse function can be categorified. So that tells us what we need in order to be able to categorify a problem of counting solutions of the KW equations. We have to be able to write these equations as critical equations for a critical point of a functional. So the KW equations have to be writable like so for some gamma, which is a function that depends on A and phi. And then the associated gradient flow equation will be a PDE in 5 dimensions on the 5 manifold R times Y4, and it will take this form. dA dt is minus delta gamma delta A, and d phi dt is minus delta gamma delta phi. And that equation has to be elliptic so that it makes sense to try to count its solutions. So we're actually asking for a lot because a generic equation isn't going to be a gradient flow equation. Sorry, a generic equation will not have, a generic PDE will not have this form. And even if it did, these equations will generically not be elliptic, and it won't make much sense to try to count these solutions. Well, actually, it's generically not true that the KW equations are equations for a critical point. That's just as well because we don't want to categorify an embedded 1 manifold and a 4 manifold. Since there's no knottedness, that wouldn't give us anything. However, the KW equations can be written as equations for a critical point if the 4 manifold is W3 times R for some W3. And if singularities are present on an embedded 1 manifold S, there's a further condition. The KW equations are equations for critical points if and only if S is contained in a 3 manifold W3 times Q with Q a point in R. So now we're back in this situation where knottedness does make sense because the knot will have to be in a 3 manifold. So to make categorification possible, we have to be in this situation that leads to knot theory. S is an embedded 1 manifold in a 3 manifold W3. So when we do take Y4 to be W3 times R, so the KW equations become equations for a critical point of some functional, we can consider the corresponding flow equations in 5 dimensions. They, quote, miraculously, unquote, turn out to be elliptic PDEs. They were also discovered by Andre Haydas and are sometimes called the HW equations. Since they're elliptic PDEs, it makes sense to hope to count their solutions and to develop a version of Morse floor theory, which would be the categorification. So naively, this leads to categorified knot invariants for any 3 manifold W3, But to justify this claim, you need some compactness properties for solutions of the equations under consideration. It's not really clear what conditions on W3 you need, and it's conceivable that a proper proof will require the Ricci tensor to be non-negative, which is a very strong condition. The case that on physical grounds one would really expect to work is the basic case of R3 that is associated to the, hopefully associated to the usual Khovanov homology and its generalization to other knots, other groups and representations. So what I've described so far is supposed to correspond to singly graded Khovanov homology. The only grading I've mentioned is the grading that's associated to the Morse index, in other words, to categorification. In the mathematical theory, you would say that the singly graded theory becomes trivial. It doesn't distinguish knots if one decategorifies it and forgets the grading. What that means here is that if we decategorified, then the embedded one manifold did not have to be in the three manifold W3. It can move arbitrarily in the four manifold, so it can be unknotted. That's the explanation from this point of view, that the singly graded theory has no information if you decategorify it. So this sentence is what I just said. The physical picture makes it clear where the additional Q grading of Khovanov homology should come from. It's supposed to come from the second Chern class integrated over the four manifold Y4. But for topological reasons, this Q grading can't be defined in the construction as I've presented it so far. The second Chern class can't be defined in the presence of the singularities we've assumed. Roughly, an instanton, well, first of all, there's instanton bubbling. An instanton could shrink to a point, but we could prevent that from happening. But we can't prevent it from instanton bubbling if the bubbling occurs along S. I've cheated, but with that explanation. But anyway, it's true topology. I shouldn't have mentioned instanton bubbling. I should simply say to define the second Chern class of a bundle over a four manifold, it works fine if the four manifold is compact. Here it's not compact because the bundle doesn't extend over S. So some topological conditions would be needed along S to be able to define the second Chern class, and the necessary conditions are not satisfied. So in precisely this situation, we do not get the Q grading. We have to do something a little more complicated. The four manifold should be a manifold with boundary, and the knot S has to be placed in its boundary. Well, I've drawn an example where S actually is a link consisting of two unknots that are linked. And then I've drawn a boundary W3. And there's a very funny boundary condition along W3 that I don't have time to describe, but it involves a singularity along W3. And then along S, there's a composite singularity, a composite of the one I've talked about when S isn't in the boundary, plus the extra singularity that you have anyway at a generic point of the boundary. So in this more complicated situation, even though Y4 is a manifold with boundary, the necessary conditions to define the second Chern class are satisfied, and you can define the second Chern class. So the boundary condition is defined by specifying a singular behavior the field should have along the boundary with a more subtle singularity along the knot. So a boundary condition defined by requiring a specified type of singularity isn't as familiar as something like Dirichlet or Neumann boundary conditions. But you can show in this case that the boundary condition does have all the formal properties of a standard elliptic boundary condition, such as Dirichlet or Neumann. So Rafe and I wrote two papers on this, actually. One with the first one without the knot, and the second one including the knot. And then Cliff has reformulated the subject in this paper. So when I say all the usual properties, for example, if we're on a compact manifold, but it has a boundary with this kind of boundary condition. So I haven't here drawn Y4 as compact, but suppose it is compactified out here. On a compact manifold, for example, the linearized KW or HW equations will have a discrete spectrum, as they would for a more familiar elliptic boundary condition. And other things you might be accustomed to for elliptic boundary value problems will also be satisfied. So the Morse-Floer theory of the HW equation with this fancy boundary condition is supposed to reproduce doubly graded Khovanov homology, with one grading being the cohomological grading and the second grading being the Q grading associated to instanton number. I think I have to mention that part of Michael Atiyah's vision about the Jones polynomial way back in the 80s was that the variable Q of the Jones polynomial would be related to instanton number in 4 dimensions. And what I'm telling you is actually a version of that, though I was a skeptic back in the 80s and for long after. The reason I was a skeptic is that Chern-Simon's theory in 3 dimensions captures a lot about the Jones polynomial, but can't be related, not in the spirit of this lecture anyway, and not, I think, in the spirit that Michael wanted, to instantons in 4 dimensions. Now, so I've perhaps whizzed through this too fast, but this is supposed to be Khovanov homology and its generalization for other groups and representations. There's also a variant of this for odd Khovanov homology. For this, you take the dual group to be spin 2n plus 1 for some n. So that means G, which is the gauge group in the description I've been giving you in this lecture, is SP2n mod Z2. And then pi4 of G is Z2. So a simple E group that has non-trivial pi4 is of type SP2n or SP2n mod Z2. So that's why I consider precisely this class of G of dual groups. So for other groups, pi4 would be trivial, but for the symplectic group, pi4 is Z2. So a G bundle over a 5 manifold has a Z2 valued characteristic class, which I'll call zeta. In the Morse-Floer theory, you can modify the definition of the differential by weighting each gradient flow trajectory with an extra factor of -1 to the zeta. And that will not affect the fact that the differential is a differential, the fact that it squares to 0. Precisely because zeta is a characteristic class. It's the factor -1 to the zeta is multiplicative in connected, I guess, in connected sums. So this is the candidate for odd Khovanov homology if you specialize to the case that the dual group is SU2, which is the same as spin 3, and the 2-dimensional representation. Well, what would be needed to rigorously define these invariants? The main thing that's needed is information about compactness properties of the KW and HW equations. So compactness properties of these and related equations has been the topic of a series of papers by Cliff Taubes in recent years. And I'm hopeful this will lead relatively soon to a proof of well-definedness and topological invariance of these invariants. If that did happen, how would we know that it was related to the Jones polynomial and Khovanov homology? I'm hopeful that there would be multiple strategies, most of which I would have no idea about. There's only one I can suggest. Well, there might be others. For example, Mina Akinadzic's work is close enough to this that it might suggest other options. But the only possible strategy that I've worked on was in the work with Gaiotto that I mentioned before, where we really didn't, well, I'll mention a paper later where others extended it to 5 dimensions, but Gaiotto and I were in 4 dimensions. We tried to show directly, without referring to the physical picture, that the Jones polynomial can be written like so, where an is the number of solutions with second Chern class, n for the KW equations. So as usual, the starting point was to stretch the knot in 1 direction. So here I've drawn a 4 manifold, which is R3, but I had trouble drawing R3. I drew a compact portion of R3, R3 times a half line. Then there's a knot in the boundary. I've called it K. It's been stretched in 1 direction. So there's occasional jumping, but generically it's independent of U. U is the stretching direction. We tried to understand what the solutions would look like after stretching. And we had a plausible scenario to recover the Jones polynomial from counting of solutions, taking into account what you could say about the stretched solutions. This has been extended to the categorified case by Galachov and more. So, and you can hope to ultimately make contact with perhaps the work of Mina Agonagic and perhaps other things. So I think that's what I have to say for today. Thank you for your patience. To summarize, I've tried to motivate without requiring too much familiarity with physics, but instead, as motivation, I assumed you were familiar with symplectic Khovanov homology, which I know was probably only a good match for a fraction of the audience. But starting with that motivation, I gave what I hope was a plausible explanation of why one would be led to study certain elliptic PDEs in 3, 4, and 5 dimensions as candidates to describe the Jones polynomial and Khovanov homology in a way that would be manifestly topological invariant if you can understand the compactness issues. And as I said, I guess that's what I have to say for today. Thank you.
Let's thank Edward Witten. Questions?
Thank you for a very nice talk, Edward. I wonder if you have any thoughts on how to reproduce Rasmussen's S invariant of knots from KW equations with numpole boundary condition.
I'm woefully ignorant. Is there any characterization of it you can tell me that I might understand? I'll be answering on the fly, regardless of what you tell me. The answer is probably no, obviously, but I guess there's.
Well, if Jake is in the audience, he can probably give more count of it, but there are several definitions. One is based on spectral sequences. I think this was the original one. Kronheimer and Moravka actually have a gauge theory definition, but that's based on instanton homology of a knot. I think they make some, connect some with HOMFLY and do something. So it doesn't look immediate to me how to connect it to.
Well, as you can see, I'm not too well informed, so I'd be happy to talk about it more, but I don't have any useful suggestion. Yeah,
the reason I'm asking is it's one of the interesting topological outcomes of Khovanov homology. So it's part of the theory, and yeah, that's motivation for the question.
I don't even remember what instanton Floer homology is. You mean Floer's original homology?
Yeah, they use.
Floer did two theories: symplectic manifolds and instantons.
No. It's instantons on 4 manifolds. So we take knot in S3 with a singularity, what we would call alpha value pi.
I know that. Yeah. Okay. Right. So I know that Khovanov and Moravka did a lot of work for SO3 instantons with a very special monodromy, where the stabilizer was O2 rather than SO2.
Yeah, that's part of that work. Yeah.
So, okay, sorry to. So the Kronheimer-Moravka paper had a mistake. I mean, there's no interpretation of this invariant with instanton Floer homology. They retracted it.
Thank you.
Sorry.
I think that's right.
But yeah, I think maybe for Edward. So there's this deformation of Khovanov homology. I mean, that was the original definition to Lie homology, where you introduce an extra differential, yes. And Lie homology is just Z plus Z. And whatever grading it lands in, it's S minus 1 and S plus 1. So S is the average of the gradings of the two factors of Z under this deformation.
I see. And can you, okay, well, I certainly don't know how to make contact with that, but that sounds like it might be, instanton homology is much farther from the content of my lecture than what you just said is. I don't know how to do what you're saying, but.
I mean, Lie homology is actually SL1. It's sort of a trivial theory, and there's a deformation from SL2 to SL1.
Okay, then I won't be able to answer the question, but I will tell you how you think about the deformation from SL2 to SL1. You don't mean SL1, you mean well, more like GL1, the maximal torus of SL2, I hope is what you mean.
Yes, yes.
Okay. So actually, such a deformation was part of my paper with Guyotto. Okay, how would you, okay, let's just discussing something more basic. So let's just suppose you're talking about the Jones polynomial. I wish I had a picture to talk about. Let's just look for a picture of a knot. Okay. All right. Well, I'm wasting time. Okay. Okay. The Jones polynomial is supposed to come by counting solutions of an equation. I described the equation on the singularity. Okay. Well, since the Jones by definition isn't categorified, but we do want the Q grading, we have to be in that case where the knot is in the boundary of a four manifold. So it's a rather complicated singularity. But anyway, we're on a half space, R3 times a half line. And there's a funny singularity on the boundary and a more complicated singularity along the knot. But then we look at solutions which are trivial at infinity, or they're as trivial as they can be given the boundary condition. I'm slightly worried about making an oversimplified statement. At least if you go to infinity, not near the boundary, the solution is trivial. Well, you can deform that and consider a solution that near infinity is not trivial, but rather has a constant one form built into it. Because the equations, wherever they were, like here, there's a one form in the equation, phi, and you can ask phi to approach a constant at infinity. Well, phi wedge phi has to be 0, so the constant is highly constrained. But for example, phi can be dx, where x is one of the coordinates, times an element of the Lie algebra. That's a good boundary condition at infinity. And it builds a projection, it builds into the story a projection of the knot to the plane. But it also builds into the story a reduction to the maximal, a quasi-reduction to the maximal torus, namely the subgroup of the gauge group that leaves phi fixed. I have no idea how to get Lie homology. I can only say that that's a good way to get various things into the picture. And if Lie homology is related to a reduction from SL2 to GL1, the first thing I would try to do would be to do something in the spirit of what I said. As you can see from the discussion, I have no idea if it would work. But if that's an example of what would come to mind that is worth trying, at least.
Sounds plausible.
Yeah, thank you.
Further questions?
May I ask a question? In relation to Seidel-Smith, are you implying that instead of Taub knot, they're using C cross C star? So they would not have a singular boundary condition at the initial point of a ray extending along the cigar.
I'm extremely forgetful. They actually describe their space in a different language. And I haven't reviewed this recently, but Kamnitzer explained in a paper I mentioned but didn't cite in detail that the Seidel-Smith space, I'm worried I have the references wrong anyway. I'm sorry, I have to apologize. But this is not, I'm not stating all this very accurately. But anyway, the space they use, although they describe it in a different language, is a space of Hecke modifications of this minimal type. So.
Yeah, I can explain the isomorphism, though I probably shouldn't try to do it here. But yeah, there's the Slotowski slices in type A, you can also write in terms of these Hecke modifications.
Well, maybe it's hard for me to know, but maybe you should say just slightly more for the rest of the audience. But
yeah, the very rough idea is, yeah, I should think about this myself. You know, that you think about these Hecke modifications. You know, so what is this doing? This is, you know, looking at a vector bundle on a disk. You know, thinking of that as a module over functions on the disk, inverting the parameter of the disk, and then choosing a different submodule in there, invariant under T. And the way to make this connection, it's hard to describe without writing everything down, is that and it's also been a little while, so I'm trying to remember. It involves looking at the action of T on the quotient of two lattices and thinking of that as a nilpotent. So like, to get two row nilpotents, you look in Laurent polynomials in C2. And when you have two lattices, one inside the other, you can look at the quotient. T acts on that, and it's always going to act by a two row nilpotent. And I'm sorry, I'm not sure I'm actually going to be able to describe this clearly off the top of my head without writing anything down. But there are several sources. I can probably pull one up and put it in the chat.
Oh, I'm sorry, I was trying to understand the physical explanation for why Seidel-Smith should be trivial at the level of polynomial, but not trivial at the level of homology.
Well, there are a bunch of people in the call who can answer much better than I can. But as far as I understand, in the A model version or Fukaya category version that they did, they literally didn't have a definition of Q.
And you were saying that the reason was that there was no boundary for the ray, so they could.
Well, I don't know if it's equivalent to what you're saying. In this, I'd better not answer in the context of their work. I can answer in the context. Sorry about the background phone ringing. In my presentation here, we only get the Q grading if we introduce the boundary to help us. We're fundamentally not like, we're trying to define the second Chern class, but we're not on a compact manifold without boundary. And the knot all by itself in the middle doesn't work, but the knot in the boundary does work. To explain that in detail, I would have to explain precisely the boundary condition on the boundary, and it's kind of a long story. But when I say it works, it actually does a little bit better than just working. If you take the quantum invariants of a 3 manifold, they actually require a framing of the 3 manifold. And if you change the framing, they change by power of Q. That gets an interpretation here because it was oversimplified to say that the boundary conditions let you define the second Chern class. They let you define it not as an integer, but as an element of a Z torsor. And that's, the Z torsor is trivialized if you pick a framing of the boundary. And it precisely mimics what's known for the quantum invariants of 3 manifolds.
Any further questions? I have a question, if nobody else does. You also studied the GL1/1.
Yes.
Did you put it in the related framework?
Yes. Well, we did GL. This was with my then student, Viktor Mikhailov, who broke my heart by leaving for biology. Unfortunately, he was brilliant. I mean, he is brilliant. Okay, we did GLN/M in general, or SLN/M, but in particular GL1/1. I'm not sure what to tell you though on the fly.
In that case, is your theory 4-dimensional?
5-dimensional still.
It's still 5-dimensional, I see.
Yes. Okay, instead of a boundary, okay. Let me try drawing, just in case I can, although I'm not good at it. Okay, so in the picture as I've explained it, we live on one side of a boundary, and there's a weird boundary condition there, which I didn't explain in detail. In the story that was related to supergroups, which were matrix supergroups, UN/M, and also orthosymplectic groups, like OSP something